Rational functions, such as f of x equals x squared minus 3 over x plus 2, often include asymptotes. The graph of this function does. In this video, I'll describe 4 steps that can be used to draw the graph of rational functions, including how to deal with asymptotes. Those 4 steps are to first identify what the asymptotes are. That comes first. After identifying the asymptotes, you'll find the first derivative, and that will give you information about where the function's graph is increasing and decreasing. Then comes the second derivative. The second derivative won't tell you where the graph is increasing or decreasing, but gives a lot of information about the graph's concavity. Once you've identified the asymptotes, intervals where the function is increasing and decreasing, and intervals of concavity, you have enough information to sketch the graph. I've described step 4 as sketching the graph based on the results of steps 1, 2, and 3. We'll now perform those 4 steps to draw the graph of f of x equals x squared minus 3 over x plus 2. There are 3 kinds of asymptotes that a rational function might have: vertical, horizontal, and slant asymptotes. Slant asymptotes are sometimes known as oblique asymptotes. First, let's think about vertical asymptotes. Vertical asymptotes occur when the denominator is 0. They occur at x values when the denominator is 0, but not the numerator. To find vertical asymptotes, you set the denominator equal to 0. And here, setting the denominator equal to 0 gives a pretty simple equation, x plus 2 equals 0. And that means that x equals negative 2 is a potential vertical asymptote. I say potential because if you would substitute negative 2 into the numerator and you would get a 0 in the numerator as well, that would indicate that x equals negative 2 is not a vertical asymptote. But here, substituting negative 2 into the numerator yields negative 2 squared 4 minus 3, which is 1, not 0. So x equals 2 is a vertical asymptote. A more detailed description of finding vertical asymptotes and horizontal and slant asymptotes is included in the description of this video. Horizontal asymptotes are based on the degree of the numerator and denominator. Again, rational functions are a ratio of polynomials, and horizontal asymptotes are based on the degree of those polynomials. And if the degree in the numerator is greater than the degree in the denominator, which is the case here, the degree in the numerator is 2 and the degree of the denominator is 1, there are no horizontal asymptotes. So we can just state that there are not any horizontal asymptotes to deal with when graphing this function. Horizontal asymptotes do occur when the degrees in the numerator and denominator are equal, or if the degree of the denominator is bigger, but that's not what we're dealing with here. Again, for more information about this, you can see the description of this video. Slant asymptotes also are related to the degrees of the numerator and denominator. Slant asymptotes only occur in one specific situation, where the degree of the numerator is exactly 1 larger than the degree of the denominator. And that's what we're dealing with here. We have a degree of 2 in the numerator and a degree of 1 in the denominator. There is a slant asymptote in the graph of this function. That slant asymptote can be found by taking the 0 of the denominator, which we already found to be negative 2, and dividing, using that, in a division. This slant asymptote occurs at y equals x squared minus 3 divided by x plus 2, where you ignore the remainder of this division. I'm going to do this division by using synthetic division. The first step in synthetic division is to take the 0 of the denominator, put it in a box, half of a box, and then I'm going to list the coefficients of the numerator. The coefficient of the numerator is 1 x to the second. Now there's not a linear term, there's not an x to the first in the numerator, so I'm going to express that as 0 x to the first, and then minus 3 is the constant. The synthetic division process requires leaving basically an empty row, then drawing a line, horizontal line, and I've also drawn a vertical line here at the bottom, and this is going to be where the remainder is, which I will ignore when determining what the slant asymptote is. The synthetic division process requires bringing down the first coefficient from the numerator, which is a 1 in this case, and then as I go up to this second row, I'll take 1 times -2. 1 times -2 has a product of -2, and as I come down the column, I'll add 0 plus -2, which is -2. -2 times -2 is +4, and these last two steps aren't important when identifying slant asymptotes because the remainder is not important, but this division turns out to be 1x minus 2. The numbers in the bottom row here represent the coefficients of the quotient, 1x minus 2, and the remainder, which can be written as a fraction divided by the original denominator x plus 2, is not important when it comes to identifying the slant asymptote. This slant asymptote is 1x minus 2. This slant asymptote has the equation y equals x minus 2. Again, the slant asymptote occurs when the degree of the numerator is exactly 1 bigger than the degree of the denominator, as was the case here, and you can find it by division. X squared minus 3 divided by x plus 2, ignoring the remainder. To do this division, I used synthetic division. You could also use polynomial long division. You would find the same quotient, of course. Y equals x minus 2. That's the slant asymptote. Step 2 is the first step that requires calculus. In the process of drawing this graph, we're going to find the first derivative. That's going to tell us all we need to know about where the function is increasing and decreasing. To find the derivative of a rational function like this, we're going to need the quotient rule. And the quotient rule states that the derivative of a fraction is the original denominator times derivative of the numerator, like the bottom times derivative of the top, minus the original numerator times the derivative of the denominator, all over the denominator squared. In the case of x squared minus 3 over x plus 2, then the derivative would be the denominator x plus 2 times the derivative of the numerator. Derivative of x squared minus 3 is 2x, minus the numerator unchanged, x squared minus 3, times the derivative of the denominator. And the derivative of x plus 2 is just 1. It's going to be pretty easy to work with because multiplying by a factor of 1 won't change anything. To simplify this derivative, I'll distribute 2x and distribute the negative through the quantity of x squared minus 3. And that will yield 2x squared plus 4x minus x squared. And then the last term is plus 3, because again, I'm distributing a negative to the term -3, which means that last term is plus 3. There is one pair of like terms to combine before calling this derivative simplified. The derivative of the function is x squared plus 4x plus 3. Now the first derivative can be used to find what are known as critical numbers. And critical numbers are x values where the graph could possibly change from increasing to decreasing. Critical numbers occur where the first derivative is equal to 0 and where the first derivative doesn't exist. The first derivative is equal to 0 when, in the case of a fraction, the numerator equals 0. The only way a fraction can be 0 is if the numerator is 0, if you have 0 divided by a number. So let's set this numerator equal to 0, x squared plus 4x plus 3. A quadratic, in this case, is equal to 0. A lot of times, when you set a quadratic equal to 0, you'll need the quadratic formula. But this one factors pretty easily. X squared plus 4x plus 3 factors to x plus 3 times x plus 1. And setting each of those factors equal to 0 means x equals -3 and x equals -1. So those are two critical numbers of this function. There's an additional critical number where the first derivative doesn't exist. That would be where the denominator is equal to 0. We actually already set the denominator equal to 0 when we found the vertical asymptote, and that was x equals -2. This function has three critical numbers: x equals -3, x equals -1, and x equals -2. Those are the only places where this graph could change from increasing to decreasing or decreasing to increasing. The only values. We can also use those values to determine exactly where this function has intervals of increasing and decreasing. And I'll do that by making a number line. And this number line is going to represent the x values in the domain of this function. And on this number line, I'm going to place the critical numbers. I'll go from lowest to highest, of course, and these three critical numbers break apart the number line into 4 intervals. In each of these 4 intervals, the graph will either be increasing over the entire interval or decreasing over the entire interval. And what I'll do to figure out whether it is increasing or decreasing in each interval is I'll choose a value in the interval. For example, the first interval from negative infinity to negative 3 includes the value of negative 4, so I'll choose negative 4. I could pick negative 5 or negative 10 or any number between negative infinity and negative 3. And when I substitute a negative 4 into the first derivative, if I get a positive value, that means the function is increasing, not only at negative 4, but at every x value in the interval from negative infinity to negative 3. Doesn't even matter what the actual value is. If it's negative, it's decreasing. If it's positive, it's increasing. Substituting a negative 4 into the first derivative, in this case, yields a positive number. Yields a positive number. If you put a negative 4 into the first derivative, you get a positive number, and that means that this function is increasing, again, not only at negative 4, but at every number between negative infinity and negative 3. Now I'm going to do a similar thing for each interval. Between negative 3 and negative 2, there are not any intervals, or there are not any integers, but I'll choose negative 2.5. And substituting a negative 2.5 into the first derivative yields a negative number, and that means that this function is decreasing between negative 3 and negative 2. After negative 2, between negative 2 and negative 1, I'll choose negative 1.5 as my test value. And f prime of negative 1.5 is negative again. So that means the graph is also decreasing from negative 2 to negative 1. How about from negative 1 to infinity? You can choose any value between negative 1 and infinity for this test value, but 0 is an easy number to work with. I'll pick 0. Substituting a 0, again, not into the original function, but into the first derivative, gives a positive number. It would be positive 3/4, but it doesn't matter what it is, just that it's positive. That tells me that this function would be increasing from negative 1 to infinity. Now I'm going to summarize this information by saying that the function is increasing from negative infinity to negative 3. I'm going to use interval notation for this. These are not ordered pairs. This is me representing the interval, the open interval from negative infinity to negative 3. And it's also increasing from negative 1 to infinity. I found that the function was decreasing between negative 3 and negative 2, and decreasing again from negative 2 to negative 1. Now I could not say that this is decreasing the whole way from negative 3 to negative 1, because remember, there's a vertical asymptote at x equals negative 2. There's a discontinuity in this graph. It's not decreasing the whole time. It's decreasing from negative 3 to negative 2. There's the discontinuity, which is a vertical asymptote. Then it's decreasing again from negative infinity, or from negative 2 to negative 1. Extrema are high or low points in the graph. High points or low points. Extrema can occur at critical numbers where the derivative was equal to 0. So in this case, negative 3 and negative 1 are possible extreme values. Remember, x equals negative 2 is a critical number, but that's a vertical asymptote. That's not a possible max or a min. A vertical asymptote is a discontinuity in the graph. There's no point at x equals negative 2 at all. If you tried to evaluate f of negative 2, you would get undefined. You would be dividing by 0. So negative 3 and negative 1 are the only possible extreme values, possible places where there's a peak or a valley in the graph. Let's take a look at both of them. At x equals negative 3, before negative 3, the graph is increasing, and after negative 3, it's decreasing. It's going up, then it gets to negative 3, and then it starts to go down. So that means that negative 3 is a high point in the graph. It's a relative maximum value. It's not necessarily the highest point the graph ever gets to, but relative to the points around it, it's a peak. Relative max. I'll abbreviate relative maximum value as just MAX. And I'm writing an ordered pair here. This is not an interval, but there is a relative maximum value at the ordered pair, -3, comma, f of -3. If I put -3 back into the original function, I'll get a value of -6 for y. F of -3 is -6. So at the point, -3, -6, there's a high point in the graph. There's a peak in the graph. Now let's check out x equals -1. Before x equals -1, the graph is going down. It gets to x equals -1, and then it goes up. That means x equals -1 is a relative minimum value. It's a low point in the graph. Again, it's not the lowest point necessarily that the graph ever gets to, but relative to the points around it, it's a minimum value. Again, I'll substitute a -1 for x in the original function. F of -1 is -2, so the point -1, -2 is a relative minimum value. Now that I've found all the information about where the graph is increasing and decreasing, I'll move on to step 3. There's more calculus in step 3. I have to find the second derivative. The second derivative will give me all the information I need about the graph's concavity, not where it's increasing and decreasing, but where the graph is concave up and where it's concave down. To find the second derivative, I'll certainly need the first derivative, and again I'll be applying the quotient rule. So here the second derivative is x plus 2 squared. This is the denominator. And the derivative of the numerator, the derivative of x squared plus 4x plus 3, is 2x plus 4. Then there's a minus sign, and I'm going to copy down the original numerator. The numerator was x squared plus 4x plus 3. The derivative of the denominator requires the chain rule. This is x plus 2 squared, so I'll bring the 2 to the front, decrease the power down by 1, and then multiply by the derivative of the inside. But the derivative of x plus 2 is just 1. So that will be pretty easy to work with. I'll have to simplify this. I'll have to do some simplifying here. The only simplifying that I'll write from the line I have above to the line I have at the bottom is just the fact that multiplying by 1 doesn't change anything in the numerator. And in the denominator, I have x plus 2 squared to the second power. You multiply these exponents to get x plus 2 to the fourth power. Something that always is going to happen when you take the second derivative of a rational function is you'll end up with a quantity to the fourth in the numerator, and that same quantity will show up in both terms in the numerator. There's an x plus 2 to the first power in the numerator, and also an x plus 2 to the second power in the numerator. So what I can do is I can simplify these. There's 4 factors in the denominator, and what I'll do is I'll cancel out a factor in both terms in the numerator with one of these 4 factors. So this will go down to x plus 2 to the third. I can eliminate x plus 2 to the first and the x plus 2 to the second. Again, I'm eliminating one factor of this quantity from all terms in the numerator and denominator, so that's going to go down to 1. So that leaves me with a situation that's a little simpler. I have x plus 2 to the first times 2x plus 4 minus x squared plus 4x plus 3. I have some algebra to do here. The next step, I'm going to multiply x plus 2 times 2x plus 4. I'll distribute x times 2x and 4, and I'll distribute 2 times 2x plus 4. And I'll also distribute not only the negative times x squared plus 4x plus 3, but I'll also distribute the 2. It'll be like I'm distributing -2 times the quantity of x squared plus 4x plus 3. And all of these multiplications are going to yield 2x squared plus 4x plus 8. This is the result of multiplying x plus 2 and 2x plus 4, and then distributing the -2 to the quantity of x squared plus 4x plus 3 yields -2x minus 8x minus 6. Realize that you're distributing the negative to all 3 terms here in addition to the 2. So a lot of like terms here. I have 2x squared and minus 2x squared. Those are going to add up to 0. And how about plus 4x and negative 8x? Those 3 terms also add up to 0. Actually, the only non-zero terms in the numerator are going to come from 8 and -6. whose sum is 2. The second derivative here is 2 over x squared minus 1 to the third power.